Now, if we have to talk about the role of friction in pure rolling, we do see that the friction plays a very important role in as far as maintaining the state of pure rolling is concerned. If there is no external force acting on a body, that is the first case wherein we might have to study the role of friction, and the second case would be, the first case would be that there is no external force, and case number two, that would be that there is an external force present. Now, both of these are very different situations and very different cases, and I would try to deal with both of them, and I hope that you would understand the concept if you haven't understood it yet. Now, say what I'll do is that I'll assume that there is a wheel or a ring or a ball or any object that can roll, say a cylinder. Let's say that there is a ring. It was given an angular velocity, which means it was only rotated with a velocity omega. Fine, this is the velocity that we gave it. Now, while giving it that velocity, we slowly place it on the ground. Fine, we'll slowly place it on the ground. Now, if we talk about this point of contact, we know as far as the ring is concerned, this point actually, this contact here, it actually has 2 points. This contact is made up of 2 points. One point belongs to the ring, that is point A, let's say, and the other point is point B, that belongs to the ground. The point A that belongs to the ring, since the ring was initially given an angular velocity omega, this point A was trying to go where? It was trying to go back. Now, since this point A was trying to go back, we know that the frictional force, it will act in the forward direction, because the point A was trying to go backwards. Now, if the frictional force acts in the forward direction, we might write it like this, F. Now, you might actually realize it in a different manner. Like what? See, we say that the center of mass, this is the center of mass. If the body has to be in the state of pure rolling, the center of mass must have a linear velocity, which is v, and it must be equal to r times omega. But we know what we had actually done with the ring was that we had given it only omega, and there was no linear velocity. It had only omega and it had no linear velocity v. Therefore, in this expression, if we talk about pure rolling, the left hand side is completely missing. It is completely zero, and the right hand side is actually present. It has some finite value because there is r, which is the radius, and there is omega that we gave it. Therefore, when it hits the ground, friction acts where? It acts forward. Now, this is actually an external force acting in a forward direction. What will an external force acting in a forward direction do? It will try to create velocity. Fine, since it's acting in the forward direction, it will try to create a velocity. Also, if you note that it will try to create a velocity where? In the forward direction. But that velocity at the start was what? 0. So I get it that there is a force, which is the frictional force. It is trying to create a velocity. That velocity, initially 0, will start to rise. It will start to increase from 0 to 1, say 2 meters per second, and then 3 meters per second, and then 4 meters per second. Fine, so that will start happening. What will be the fate of this omega? Well, we know here that omega is actually a clockwise angular velocity, and this f, if we see that it will give a torque which is an anti-clockwise torque about what? The center of mass. Now, if it gives an anti-clockwise torque about the center of mass, it means we have an anti-clockwise torque about center of mass. An anti-clockwise torque about the center of mass would mean an anti-clockwise alpha angular acceleration. This anti-clockwise angular acceleration will actually try to reduce the value of omega because omega is clockwise. So this friction is actually trying. Ho! So this friction is actually trying to do what? It is trying to increase the velocity of v from 0 to some finite value. It is trying to decrease the value of r omega. Fine. So I understand that with time v will start increasing and r omega will start decreasing. If that happens, let's just say this is v and this is r omega. Let's just say initially v was 0 and there was some finite value of r omega, say 10 meters per second. Now when the time passes, v becomes 1. Say this becomes 9, v becomes 2, say this becomes 8, and v finally becomes 5, and this becomes what? 5. There will be a point when both will get equated, and when that happens, we'll say v is equal to r omega. As soon as v is equal to r omega happens, we say that this particular ring starts to be in a state of pure rolling. And if it starts to be in a state of pure rolling, which means these 2 points A and B, there will be no slip at this point. There will be no slipping at this point. And if there is no slipping at this point, which means friction now will not act at all. So friction was required to create pure rolling, but as soon as pure rolling started, friction vanished. At that time, frictional force will be equal to 0, but not before that. So frictional force will become 0 only when pure rolling has been initiated. I hope this has cleared some amount of it.